So let's start with trying to prove that f restricted to u inverse is differentiable. So we've got all that stuff above, and I'm going to start with this first bullet point. So let's fix a point, y0, in V. Then our goal is to prove that f restricted to u inverse is differentiable at y0. I guess it's better to write we will prove. That this is differentiable at y0. Okay, so how do we prove a function is differentiable? Well, we have to have a guess as to what the derivative is, right? So here's a picture of what is going on. So here's, I'm going to stop drawing E. How about I just draw U? Instead of drawing E with U inside every time and then having this really tiny drawing. So here's U. And this is f restricted to U, and it's a bijection to V. And I'm drawing U like a disk because it was literally defined to be a ball, although that doesn't really matter anymore. Okay, so f restricted to U is this bijection. And sitting here at the center, although that doesn't matter so much, of U is A. And x, somewhere over here is f of A. And f of y0, y0, is somewhere over here in V. Since f restricted to U is a bijection U to V, there's some x0 back here, which gets mapped over to y0. So there's some. Actually, I don't have to say there is some. I can just say exactly what it is. Let x0 be the inverse of f restricted to U, which exists, evaluated at y0. So that we now have f of x0 equals y0. Okay, and we're trying to prove, so going back the other way, we have f restricted to U inverse, right? And we're trying to prove that this thing is differentiable at y0. So what do you think might make a good linear approximation to this function near y0? Well, this function has a linear approximation near x0, right? Because this function is differentiable at x0. So if we could invert the linear approximation to this function at x0, then that might make a good guess for what the linear approximation to the inverse of this would be at y0. So that's the idea. So we would like to prove, so we will show that f restricted to U inverse is differentiable by showing that its derivative, so we're going to show it's differentiable at y0 by showing that its derivative at y0 is what you get if you take the derivative of f restricted to U. I don't have to write restricted to U, just the derivative of f at x0 inverse. So this is our guess as to what the derivative is. But hang on, do we know that this is invertible? Do we know that this linear map here is an invertible linear map? That was not the assumption in our inverse function theorem setup, right? The assumption, way up here at the beginning, is that f prime of A is invertible. And in our special case, f prime of A is the identity. And A is just this specific point that U is a neighborhood of. So we need to put some effort into proving that f prime of x naught is actually invertible. Now for this, it actually does matter. So the idea is that if f prime at A is the identity, and U is very small, then x naught will be close to A, and so f prime of x naught will be very close to the identity, since f prime is continuous at A. And a linear map that's very close to the identity should be invertible. So that's the idea. And we will be able to prove that a linear map close to the identity, or a linear map close to being very close to an invertible one, should be invertible. But for that, I should have actually mentioned the origins of U. So I'm going to go back up here to where I listed the things we have and what we still need to prove, and add in here what U actually was. So let me add that in green. So U was a ball of a certain radius, which we had called delta, centered at A. And it had this property. I guess it doesn't matter that it's a ball anymore, but it does matter that it had this property. The delta, the radius of that ball centered at A, was chosen so that for x in U, f prime x is in a ball of radius 1/2 centered at the identity map. So that is how U was chosen, and that's how we got this property down here. Or that helped to get this down here. So that was the point of U. Okay, so for x naught down here, x naught is going to be close enough to A that f prime of x naught is going to be within 1/2 of the identity. So here's the question before we try to show this, is this linear map invertible? And the answer is yes, which I'm about to prove, because, well, let's write in a full explanation. Yes. Why? Okay, so why is f prime x not invertible? So we know, since x naught is in U, by the very choice of U from the very beginning of the proof, f prime of x naught is within 1/2 of the identity. So now suppose H is some n-tuple, some vector in Rn, which f prime of x naught kills. So f prime of x naught sends H to 0. Then I'm going to prove H must be 0. This will prove that f prime of x naught is injective and therefore invertible. So remember, for a linear map from a vector space to a vector space of the same dimension, like f prime of x naught here, injective and surjective are equivalent to invertible. Individually they are. So injective is equivalent to invertible, and surjective is equivalent to invertible. So I'm going to prove that f prime of x naught is injective. Okay, then in this situation, let's do it this way. So let's look at the norm of H. One way to write down the norm of H is like this, f prime x naught minus the identity map on Rn of h. So this is a way of writing the norm of h. I guess I introduced a minus sign here for some reason, but it doesn't matter because there are norm bars. So this is a way of writing the norm of h, because this, when this linear map hits h, it'll kill it. And then identity on h is h. Okay, so this is bounded above by the norm of this linear map. So you see what I'm doing. I'm just forcing this term in because this is what I have control over. I know that it's less than 1/2. And look at this. Well, I guess I should say less than or equal to, since I'm trying to prove h is 0 actually anyway. So this thing here is less than 1/2, and so the norm of h is less than or equal to 1/2 of itself. This can only happen if the norm of h is 0. Which can only happen if h is 0. So this is injective. And therefore invertible. Okay, so we can now talk about f prime of x naught inverse. So we can start trying to prove differentiability of this function at y naught with our guess that the derivative is going to be this. Okay, so what is it exactly that we need to prove then? So we will prove that, so now I'm going to use the definition of derivative. So I need to prove that a certain limit equals 0, right? And the limit goes like this. So this is for differentiability of the function f restricted to u inverse. And I'm talking about differentiability at y naught. So let's do y naught plus k here. And it'll be limit as the vector k goes to 0. Norm k down here. And then this is the function whose differentiability I'm looking at. I'm looking at differentiability at y naught. And then here, I'm going to put in what I think is the derivative linear map, and then evaluate it at k. So let me remove that ugly box. So like this, here I'm going to put what I think is the derivative. I think the derivative is f prime of x naught, which is a linear map, inverse, which exists by the argument made right here. So this is the goal, is to show that this limit is 0. Let me fix that. Okay, so let epsilon be greater than 0. Then we must show that there is a delta. And to make the notation look pretty, I'm just going to call this delta, even though there was a delta before. I think I didn't write it here, but very, very early on when we were choosing u, we made u be a delta ball centered at x or something like that, or centered at a. Forget that delta. I would like to use delta for a different purpose now. So delta is now going to be used for the sake of trying to prove that this limit equals 0. Okay, so then we must show that there's a delta greater than 0, such that whenever k is smaller than delta in length, and y naught plus k is in the domain of this function, so and y naught plus k is in V, we have this. So I'm going to write down the numerator here, and I'm going to write everything down in a way that doesn't have the division, which is kind of nicer. nicer to work with, I think. So linear map at k and norm bars. And then I'm trying to show that this is less than or equal to epsilon times the norm of k. So if you're wondering why I didn't do this and why I put less than or equal to here rather than less than, then you might want to look back at that lecture where I talked about different ways of dealing with this limit and talking about differentiability. So that was lecture 1, part 3, if you want to know why I'm not including those things. So now I want to draw a picture again and include these various new components that are showing up. And part of the reason for drawing the picture is that it helps to motivate defining important quantities and giving them notations. So here's our set U. And you know, I don't really care about the center point A anymore. I'm not even going to include that in the picture. That has basically served its purpose already. So somewhere inside U we have x naught. And here we have f restricted to U. And here's V. And somewhere in V is y naught. And f sends x naught to y naught. Now, for any given k, so we're going to have to be working with these k's, right? We're going to try to show that if we make k small enough, then we can get this thing over here to be small enough per k. So given any particular k, such that y naught plus k is in V, we're going to have this other point, y naught plus k, and a corresponding displacement vector here, which is k, right? So when you're picking a k, you're sort of picking a displacement to the input of the inverse. So it looks like a displacement over on the output side of f. Okay, so when you pick k, this is what I imagine, that it's a displacement vector pointing away from y naught. And when you're talking about differentiability, you're looking at displacement, like k, to the input of f inverse, which is over here. And you want to look at the corresponding displacement in the output of f inverse, which is on this left side, where you see, which looks like the input space for f. So y naught plus k, that's going to be a point in V, right? So that means there's some point in U that maps over to it, right? Like, just apply the inverse of f to this point to get a point back here that maps over to it. Then there's also going to be a corresponding displacement here. Let's call this displacement h. So k stands for displacement to the input to f inverse, and h stands for displacement to the output to f inverse. H depends on k, so I'd like to make the notation work like this, h sub k. And then if I call this displacement vector h sub k, then it makes sense to call where this ends up x naught plus h sub k. Okay, so I just want notation that gets this picture kind of going. So here comes the notation. So first, fix k in Rn, I guess it's an n-tuple, such that y naught plus k is in V. And I'm not saying anything about delta. I haven't defined delta, right? All I'm saying above is we must show there's a delta, so that whenever k is smaller than delta in length, then good things happen. So I'm going to fix k and then just start a discussion about a particular fixed k. Then I'll go back and find out what delta should be, what kind of delta will work. Okay, so fix k, so then we've got this part of the picture and notation for that part. And how's this part going to work? Well, define, for any fixed k, define h sub k as follows. H sub k will be whatever, well, basically it'll be this point minus this point, right? That would be the displacement vector there. So what is this point? This is the point that f sends to y0 plus k. So this point is f inverse applied to y0 plus k. So f inverse applied to y0 plus k. So right here, this is this point. And then I'm subtracting x0. Okay, so that's hk. And then by the definition of hk, if you just add x0 to the other side, you see x0 plus hk equals this, which is a point that gets mapped by f to there. Oh, so another way of looking at it is like this. Just write x0 in terms of the way we originally defined x0. x0 was just whatever point f sends to y0, whatever point in u f sends to y0. And then if you look at this expression here, this should look kind of familiar. This came up back here. Or up here, yeah, right up here, where I say, then we must show what we want to show. We fix epsilon greater than 0, then we must show there's a delta such that when you make k smaller than delta, we have this. And right here, this difference, this is the quantity that we just defined to be h sub k. This is the quantity we defined to be h sub k. So we're trying to show that h sub k is very close to what you get if you apply this linear map here to the vector k. So in order to do what we want to do here, in order to do this, we need to somehow use the differentiability of f, right? So that's got to come in somehow, the differentiability of f at x0. The thing is, the differentiability of f at x0 tells us about, it gives us information when we make h sub k small, right? The differentiability of f at x0 gives us useful information about what happens when we make displacements away from x0, so this h sub k, small. But we don't control h sub k directly. In this situation, we're given control over k, not h sub k. So we're given control over displacement to the output. But we only get useful information out of the differentiability of f if we control displacement to the input. So what we must do is find a way to control h sub k by using k. So we need some way to show that if we make k small, then we correspondingly make h sub k small. Then we can benefit from the differentiability of f at x0. Okay, so what will help us to do this, to control h sub k by using k, is, going way back, this tool that we have, phi sub y. So remember this family of maps, it has these two really great properties. So we're going to make use of that, and we're going to make use of this property. All right, so that property that I pointed out up there is about any 2 points in U. It says that the distance, if you take any 2 points in U, then phi of one point, the distance between phi of one point and phi of the other point is going to be bounded above by half the distance between the 2 points. That was this. For any 2 points in U, this. And this works for phi sub y for any y. And I'm going to specifically focus on phi sub y naught. So, yeah. Let's see. We have phi sub y naught. And then I can apply this to any 2 points in U, and I'll get this nice inequality. So the 2 points I choose are x naught and x naught plus hk. Remember, in this discussion, k is fixed. So x naught plus hk, x naught. And then here, when I do x naught plus hk minus x naught, I just get hk. So this is the property that we have from above. And if you use the definition of phi and work out what this is, this thing here is, let's see, y naught plus f of x naught plus hk minus x naught plus hk, or I think I got my signs off there. Maybe, I think it was this. And then this one is y naught minus f of x naught plus x. And we get some cancellation. So I guess it didn't really matter which phi we used. So we can use phi sub y naught, but it doesn't really matter which one we use, huh? Just use any of them. Why didn't we just use phi sub 0? I'm actually not sure. Yeah, I don't see any reason not to just use phi sub 0, but whatever. Let's just go with it. So, more cancellation. This was x naught. That's a typo. And this should cancel that. Okay, so overall we have positive f of x naught minus f of x naught plus hk plus hk. And this here, f of x naught minus f of x naught plus hk. So just look at the picture. F of x naught is y naught, right? F of x naught plus hk is y naught plus k. So this thing I underlined in green is this displacement vector. That's actually k, right? Although I think it's backwards. K would be f of x naught plus hk minus f of x naught. So k would be y naught plus k minus y naught. Okay, so the thing I underlined in green is actually minus k. So we got, let me write it like this, hk minus k. Okay, so overall we have the distance between hk and k is less than or equal to 1/2 the length of hk. So let's write what we overall got. So look what we can do with this now. This will give us a way to use k to control hk. So if you look at hk, use the triangle inequality. And this thing is less than or equal to 1/2 hk. Then overall, subtract 1/2 hk from everything there. So I get 1/2 hk is less than or equal to k. In other words, hk is less than or equal to 2k, like that. Okay, that is awesome. So now we can control hk by controlling k. Okay, so that's really good. Again, that's because it's really good because controlling hk, making hk small, gives us the ability to use the differentiability of f at x0. So now we can make hk small by making k small. Okay, so now I want to end this fixing k. Stop fixing k now. So forget about k, the k that we fixed. So let me recap what we did a little bit. We are trying to prove we've already fixed epsilon greater than 0, and we're trying to show that there's a delta that works. Where works means we get this inequality for all k smaller than delta. Then we fixed k, and we defined, for each k, we've defined this object, h sub k. And we fixed k and showed that this inequality holds. So starting here, we fixed k, then we proved this inequality. This is like its own claim. So end there. All right, so now let's use the differentiability of f at x0. Okay, so remember we have fixed epsilon greater than 0 already, and we're trying to find delta. So since f is differentiable at x0, there is some delta 1, I'm going to call it, because that's not exactly going to be our delta, but there's some delta 1 greater than 0, so that whenever a displacement vector h is smaller than delta 1 in such a way that x0 plus h is in E or U, doesn't really matter. We have, and then here's what it provides. F of x plus h minus f of x minus f prime, sorry, x naught, not x. F prime of x naught applied to the vector h is less than or equal to epsilon times h, except I don't want to use that epsilon I fixed at the beginning. I'm allowed to put any positive number I want here, so I'm going to put epsilon 1, where epsilon 1 equals, and I'm going to decide later what it is. So we'll fill in that box later when we find out what should go there. So this is using the differentiability of f at x0. Okay, so this is what I meant by making a displacement to the input h small is how we can make use of the differentiability of f. And I can make the displacement vector h small by making k small. So that's what we achieved here when we showed h sub k is always bounded above by 2k in norm. So the delta that I pick is going to be how small k ends up being, right? So let me pick delta to be 1/2 delta 1. That 1/2 is to cancel that 2 up here, as you will see. Now I'm going to fix k again. So let k be some n-tuple such that the norm of k is less than delta, and y0 plus k is in V. Okay, so this picture is now in place with specific points, y0, y0 plus k, and these things are now defined. Then, making k this small, let's just point out that guarantees that h sub k is also sufficiently small. So h sub k is less than or equal to 2 k is less than 2 delta, which is equal to delta 1. So the 1/2 here cancels that 2 there. Okay. So that means we have this stuff except for the displacement vector hk, h sub k. So that is what we have. And by the way, what you're looking at here, f of x0 plus hk minus f of x0, x0 plus hk is y0 plus k. Or f of x0 plus hk, that's just y0 plus k, right? And f of x0 is just y0. So by the definition of hk, that difference, f of this point minus f of this point minus this point is k. So what we are looking at here, this difference, this is k. And let me write down also what we want to show. So from back here, what we need to show is this inequality here, right? And it involves hk. So we're trying to show that the distance between hk and this thing is less than or equal to epsilon times the norm of k. So let me go write that down so I have it to stare at while looking at this. We must prove that the distance between hk and this is less than or equal to epsilon times the norm of k. So I hope this also feels right as we write it, and it's not just a bunch of symbols for you. Basically, this is saying we need to prove that, so hk, that was a displacement on the input side of f, right, on the left side of the diagram. We need to show a displacement on the input side of f, which is a displacement on the output side of f inverse. So a displacement to the output of f inverse can be approximated by this linear map. That's what we're trying to show to get differentiability of f inverse. So to make it maybe more clear what we have versus what we want, let me write this as k. This difference here is k. Let me just write that. So we know about, so we can we can make this small by choosing epsilon 1 up here. So we can make k close to this. And we're trying to make, how about I even write this the other way around? So there's norm bars around here, so I can flip this subtraction and it won't change anything. Yeah, so look at the difference between what we have and what we want. This is what we have. We can control this. What we want is to control this. They differ only in that one has had the linear map f prime of x naught applied to it, right? That's the only difference. So, let's do this. Now I think it's more clear what to do. So this thing that we're trying to show is less than epsilon k. We can make it look like this by applying f prime x naught and f prime x naught inverse. So let me put it this way. Oh, sorry, prime here. Let me think of it like this. I'm pulling out f prime x naught inverse. And to make this work, I must have f prime x naught being applied to hk. Like that. So just check that you agree with this, that if you distribute this, apply it to both of these, then you get hk for the first term and then this thing for the second term. Okay, so you see why I'm doing this. I'm trying to force this to appear. So now, this is no bigger than that. And now I can use what I've got here. So this portion here is bounded above, so it's this, and it's bounded above by epsilon 1 h sub k. Epsilon 1 norm hk. And that's not really what I wanted. Remember, I wanted this at the end. So I wanted something times the norm of k. But remember, again, we managed to set things up so that controlling k controls hk. Controlling the size of k controls the size of hk. So this is bounded above by 2 norm k. And now it's clear what epsilon 1 has to be in order to get this that we want at the end. So at the end we want, well, it'd be nice to have equals epsilon times k. So what should epsilon 1 be? It should be 1 over 2 times this. So now I can go back and pick epsilon 1 and fill in the blank up here. 1 over 2 times the norm of f prime x naught inverse. So that should work. And that's definitely a positive number, and I'm not dividing by 0 because f prime x naught is the inverse of a linear map, so it is itself an invertible linear map. And so it's not the 0 linear map, and only the 0 linear map has norm 0. All right, so I would say that's it for, well, I guess I don't get to put the box yet. That's it for that part. So let's go way back. We have now proven, we fixed y naught in V, and then we proved that f restricted to U inverse is differentiable at y naught. This was for arbitrary y naught in V. So we have proven that f restricted to U inverse is differentiable on V. So thus f restricted to U inverse is differentiable on V. And what is left for us to do now is to prove this continuity of the derivative. So we will work on that in the next video.